some equations. So section 6.6, solving equations. 2 log base 5 of x equals log base 5 of 9 is our original problem for the first one. Okay, so the goal here is to look at the problem and see what's in there. If there's a log on each side, but only a variable inside of that log on one side, then you just need to get rid of the logarithms, and then we'll have an easy equation to solve. So for this one, we've got log base 5 on each side. The left side has an x inside of that log. The problem is that 2 is hanging out in the front. Is there a log property that would help us get rid of that 2 in the front? What's it do? Yeah, it turns it into an exponent, so it's log base 5 of x squared. So log base 5 of 9. Okay, so if it's log base 5 on both sides, then what do we know about the things inside the logs? If it's log base 5 of x squared and then log is equal to log base 5 of 9, what do we know about x squared and 9? They should be equal to each other. What's the math that gets rid of the log base 5? You mean exponentiate with a 5 as the base? I think that's what you're trying to say there. If I exponentiate with the 5 as the base, that's going to get rid of the logs. That's the math that says, hey, now x squared does equal 9. That's what's happening here. We get rid of the logarithms. We get x squared is equal to 9. And then what do we do from there? Square root of both sides. Plus or minus 3. So we get x equals positive 3 and x equals negative 3. Those are the answers we found. What do we have to remember about logarithms, though? We can only take the logs of what kinds of numbers? Positive. So if I go back to the original problem, I've got log base 5 of x in there. If I put positive 3 in there, is that okay? Yeah. If I put negative 3 in there, no, not okay. Can't do that. So there we have a log of a negative. So we found that it's an extraneous solution. We would throw it out. Okay. Go back to your original problem before you've done anything to check those. Okay. Not too difficult. That's pretty easy. Let's get a little bit more involved. Something a little more fun. Log base 5 of x plus 6. Log base 5 of x plus 2 equals 1. This one's a little different. It doesn't have a log on each side now. It's got 2 logs on the same side and then a number on the other side. Okay. Well, how could I turn 2 logs on one side into 1 log? Okay, so this is log base 5 of x plus 6 times x plus 2 is equal to 1. Or you could rewrite that log base 5 of x squared plus 8x plus 12. That would. You don't have to do that at some point anyway, so let's do it now. Excuse me. Now, we've got a log on one side and a number on the other. Excuse me. So if we got a log on one side and a number on the other, how can we get rid of that logarithm? Okay, we could exponentiate with a 5. Yeah, that would work. We could also just rewrite it as an exponential using the rules. You know, this is the base. The 5 to the first power is equal to whatever you're taking the log of. It's the same work. It gets you the same result. I like the idea of just exponentiating because that seems consistent with what we did on example A, right? Is that to get rid of a log, we can exponentiate. And these cancel, and there we get x squared plus 8x plus 12 is equal to 5 to the first power, which is what? Just 5. Okay. Now, how do we solve that problem? Subtract 5, get it equal to what? 0. We got x squared plus 8x plus 7 equals 0. It's a quadratic, so we got several options in solving that. I'm going to use factoring because I know that x plus 7 and x plus 1 is equal to, it's how that factors, because it needs something that multiplies to be 7, that has to be 8, and that'd be 7 and 1. So I'm getting those. Set those equal to 0. Pretty easy solve there. -7, -1. Both of them are negative, but do I just throw them both out because they're negative? No. What do I have to do to decide if I even throw any of them out? Plug them into the original problem and see if they give us a log of a negative. So if I plug in -7, -7 plus 6 would be -1. So there's a log of a negative. We know the -7 is out because it messed it up in the original problem. Gave us the logarithm of a negative number. We can't do that. Okay. If we plug in -1, -1 plus 6 is 5. That's okay. We can do that. And then we plug in a -1 here. -1 plus 2 is 1, and that works too. We got a positive number there. So as long as you end up with a positive number inside the logs, you're okay. So that one checked, and we're going to keep it. So x is equal to -1 is the only answer for this one. I'll go ahead and caution you. You're not always going to throw out one of the two answers. You're not always going to throw out any of the answers. Sometimes you'll keep both of them or all of them that you find. Sometimes you might even throw out all of them. They both, that you can find answers, but they don't work in the original problem. So you could have a no solution type situation. That does happen sometimes, but it's that's fairly rare. All right. Let's do another one. Let's change bases. Let's do natural log of x plus natural log of x minus 4 equals natural log of x plus 6. A lot of natural logs in that one. Not yet. Because how many are on the left side? 2 of them. And there's 1 on the right side. So we need to get at least these 2 combined back together, right? So how are they going to combine back together? Natural log of x times x minus 4. And then this is natural log of x plus 6. So I'm showing an extra step here. You probably would go ahead and just multiply x times x is x squared, and x times the 4 is 4x. You would probably go in. I'm throwing that extra step there just so we can see that this is where x squared minus 4x comes from. And then Kylie said that they're going to cancel out, which is true, but how? E is the what? The base. We're going to exponentiate like we've done in the last 2 problems. The base was 5 in the logarithms. We exponentiated with that base. Here it's natural log. The base is e. So if we exponentiate with an e, that's going to cancel out the natural log on each side. Okay. Now, some books, if you go watch some examples online, like you go to Khan Academy or something, at this step, they may skip saying that. They may just say, oh, you just set these 2 equal to each other, which is true. It's what you're doing, but this is the math that's making it happen. And I like to show that just so when we get to problems where they don't have a log on each side, that you know, oh, okay, this is what's going on there. All right, so we got x squared minus 4x equals x plus 6. So move the x over. X squared minus 5x equals 6. Okay, how do I do that? Okay, so if I subtract 6, and then we get all the options of solving the quadratic. We get quadratic formula or factoring, whichever way you want to do that. If we did quadratic formula, just because we did factoring on the last one, this one will factor too, but what if you just didn't know that? And you just automatically did this. Be 25 plus 24 over 2, which is 49, which works out great because we know the square root of 49 is 7, right? So 5 plus or minus 7 over 2. So x equals 5 plus 7 is 12, divided by 2 is 6. And then 5 minus 7 is negative 2, divided by 2 is negative 1. All right. Now, we've got to go back and check those to make sure we don't get a negative inside of the square root. So plugging in 6 looks like it's going to work. Natural log of 6, natural log of 2, that's good. On the other side, we got natural log of 12. That's okay. If I plug in the negative 1 into the original problem, the very first one, red flag, can't use that. Natural log of a negative is not possible, so we throw that one out. So 6 is the only solution that we find. Okay. So with the logarithm inside of the equation, if you got a logarithmic equation, to get rid of those, you're going to have to exponentiate. Okay. Now, the next type problem is not logarithmic. It's exponential. And it's not like the exponentials we did earlier in the chapter. Because the ones we did earlier in the chapter, we could do something, we usually have like a 4 over here where the 5 is. We have a 4, 16, 8, 32, 64, something that we could rewrite as 2 to a power. This one, we can't do that. So we want to try to solve this and get that x out of the exponent area. Okay, so how could we do that? We did something like this, but not this. Say it again. No, ma'am. It's 2 to the x. It's not 2x. So we've got to get that x out of the exponent. If I do, what log do I use? Base 2 to get rid of the base of a 2 on the exponent stuff. But if I do that on one side, rules for exponents are I got to do that on the other side. And these will cancel each other out, leaving just x is log base 2 of 5. We'll get a decimal approximation for that. Log base 2, math, log base 2 of 5. You go 4 decimal places, so 2.3219. There's our exact solution and a decimal approximation for that. Not too bad. That's pretty easy. They obviously get harder. So, what if they had a number in front there like 8? 3 to the x equals 5. So where's the exponent at? The x is on the 3, right? So how do we get rid of the 8? It's in the way, right? Because it doesn't have an exponent. Divide by 8, so we get it out of the way. And that would allow us to do what? To get rid of the, or get the x out of the exponent area. Okay. It's not an exponentiation because it's an exponential. You take the log base what? 3 of each side. These cancel out. Log base 3 of 5/8. We'll get a decimal approximation for that. Four decimal places, 4, 2, 7, 8. The one makes it stay the same. So negative 4, 2, 7, 8. Yeah, 4, 2, 7. So there's another good. All right, let's get one that's a little bit more complicated. Obviously, I can't do an example like every single problem you'll ever encounter, but try to do some generic stuff here. This one's a pretty tough one. I definitely wanted to show you one of these. Well, here we have different bases with exponents with a variable on each side. So this is one of the classes in the past who said this is the toughest ones in this particular section. If the bases were the same, they're the easiest ones. But the bases are different, so that makes it a little tougher. Now, when those bases are different like that, you've got a variable in each exponent, then using log base 5 would only get rid of the 5. Using log base 3 would only get rid of the 3. So there's not a nice happy medium to that. You know, you couldn't use log base 15. It's not even related to either of them. It's related in number wise, but not exponential wise. So what we want to use is one of the common logs. And this particular textbook, and most, I won't say all textbooks use this, the natural log, but a lot of them do. So when we have different bases, we want to use the natural log to get those exponents down. Okay, so we're going to use natural log on each side. So we're going to take the natural log of each side. And I'm going to kind of try to show every step on this one. Okay. And that natural log, now it's inside of a logarithm. Since we did it on both sides, it makes it legal. Now I can take this x minus 2 and pull that whole exponent down to the front. Okay. So I've got x minus 2 times the natural log of 5. And then on the other side, the same thing's happening. I got 3x plus 2 times the natural log of 3. Now, here's the tricky part. What is natural log of 5? In general, what is it? Not specifically like what's the decimal for it, but what kind of thing is it? It's just a what? Well, it's not an exponent. Natural log of 5 is it's just a number, right? Okay, so if it were like a 13 out there beside that, what could you do with the parentheses and the number beside it? Distributive property. Well, we can do that with this, even though that's a natural log of 5. We're going to distribute natural log of 5 to both of those. And on the other side, we're going to do the same thing with natural log of 3, because now it's distributive property, which will allow us to do that. So here we have x natural log of 5 minus 2 natural log of 5. And on the other side, we got 3x natural log of 3 plus 2 natural log of 3. So we've distributed the natural log, which is just a number, to both terms in the parentheses. Looks like we're making it more complicated, but we've got to, in order to get our variables isolated, okay? So what are we trying to solve for? X. So if we're going to try to solve for X, where do all the X things need to be? On one side, and all the things that are not X's need to be where? On the other side, okay? So here I've got an X natural log of 5, and then I've got this piece that doesn't have X. So I could get rid of this, right? By doing what? Adding it over here to the other side. And then this guy's got an X. It needs to be over here with this X, right? So how would I move this? I could subtract it. So in one step, I'm going to do both of those things. Okay, I'm going to add 2 natural log of 5. And then I'm going to subtract 3x natural log of 3. Okay. That's going to cancel. That's going to cancel. That's going to give us x natural log of 5 minus 3x natural log of 3 equals 2 natural log of 3 plus 2 natural log of 5. Okay, so we've rearranged this so that everything that has an x is on one side and the stuff that doesn't have an x is over here. All right, couple more steps and we're there. What are we trying to solve for again? Okay, where's x? On both of those terms on the left side, right? Think Algebra 1. How could I get that x off of both of those terms? As a greatest, exactly. Good, good, good. We're going to pull out an x as a greatest common factor on these two. Because natural log 5 is just a number. Technically, this 3 in front, it's 3 times natural log of 3, and that's a number. The x is just kind of in the way. So if we factor that out as a greatest common factor, this other side hadn't changed any. Now, what's this thing? In general, what is it? It's a number. It's an ugly decimal number, but it's a number, okay? So what's going on between x and this number? They're multiplying, and the opposite of that would be dividing. So divide by the number. This side's going to cancel out. There's x by itself. 2 natural log of 3 plus 2 natural log of 5 divided by natural log of 5 minus 3 natural log of 3. There's the exact solution. It'll never pop up there. There we go. 2 natural log of 3 plus 2 natural log of 5. That's the blue numerator here. We divided by this number, so there's that number. There's the exact solution of that. There's not really anything you can do to simplify that in the exact solution part, but we can get the decimal approximation for that. So with it being a common log, that makes getting the decimal approximation a little quicker. Not much, but so we go to the calculator, we're going to use natural log. So we got 2 natural log of 3. Don't forget to close. There we go. Don't forget to close the parentheses after your 3. If that's a common mistake to not do that. It'll think, oh, we're still taking the natural log of something. So don't forget to close those parentheses. And then we have plus 2 natural log of 5. And there went my screen. Why does this always happen at 9 o'clock? Y'all know? I don't know if the room is. I may be. All right, so we got, this is the numerator. We're going to get that answer. And then we're going to divide that by that denominator. So I'm going to hit divided by, and then parentheses, natural log of 5 close parentheses minus 3 natural log of 3. You could do that all in one typing expedition if you wanted to, but I chose to do it in 2. So what this does, if you just hit the divide symbol on your graphic calculator, that's taking this answer and dividing it by whatever I'm typing next. And I've actually typed all that and still not there. So, all right, there it is. So we're going 4 decimal places, negative 3.211. The 3 makes the 6 stay. So 3.2116. Negative 3.216. There's our exact solution and our decimal approximation. That's as tough as they get, guys. They really don't get any harder than that for a problem that you're going to have to use a log to solve. And got one more example. Maybe we can make it through it.